We're not talking, especially if you have a Chromebook out in front of you. When you're done with the quiz, put the Chromebook away and take out your Unit 5 review, please. And the review begins on page 29 in the packet. So open it up to page 29. You can actually pack up your Chromebook. You won't need it anymore today. Put it away. Just take out your Unit 5 packet. Perhaps your reference tables and calculators. Something to write with so we can go over it. All right, just take it later. I don't want to hold up the class to review. All right, starting on page 29, let's check your answers. Question 1. What does it mean for an object to be traveling in 2 dimensions? It means that it's moving both horizontally and vertically simultaneously. Number 2, describe what happens to the horizontal component of velocity when the object's in the air. It's going to move at a constant speed. Number 3, if an object is traveling at a constant velocity, how does its average velocity compare to its instantaneous velocity throughout the trip? It's going to be the same. The average, the starting, and the ending velocities will all be the same if it is constant. Number 4, which equation should you be using to make calculations about a projectile's horizontal displacement, meaning its range, and its horizontal velocity? You're going to start with d is VIT plus half AT squared. You're going to drop out the a, 1/2 AT squared term because a is 0, leaving you with just the displacement is the initial velocity times the time. So the initial velocity is the displacement divided by the time. Number 5, what 3 equations can you use to make calculations about a projectile's vertical motion? You have 3 of them. They are VF is VI plus AT, VF squared is VI squared plus 2AD, and D is VIT plus 1/2 AT squared. I just added Y subscripts to everything, but you don't have to do that. Nothing cancels out, by the way. Number 6, let's sketch the motion of a horizontally launched projectile on the axes where we are looking at our vertical position versus our horizontal. We get this parabola as it comes down to the ground. Number 7, 2 balls are released from the same height, but one is dropped and the other is launched horizontally. Why do they reach the ground at the same time? Because they are moving through the same vertical distance, and the vertical acceleration of gravity is the only thing acting in the vertical direction. The horizontal velocity has nothing to do with it. Any questions on that page? Okay, let's check the multiple choice. Number 1 is 1. Number 2 is 3. Number 3 is 1. Number 4 is 2. 5 is 3. 6 is 4. 7 is 3. 8 is 3. 9 is 1. 10 is 2. 11 is 4. 12 is 1. 13 is 2. 14 is 4. 15 is 3. 16 is 1. 17 is 4. 18 is 4. 19 is 4. 20 is 3. And 21 is 4. 22 is 1. 23 is 3. 24 is 4. 25 is 4. 26 is 2. 27 is 1. 28 is 4. 29 is 2. 30 is 1. 31 is 1. 32 is 4. 33 is 4. 34 is 2. 35 is 3. 36 is 2. 37 is 1. 38 is 2. 39 is 2. And the last multiple choice, 40, is 3. All right, let's go page by page to see what questions you have. Let's start back on page 30, please. Anything, and we'll do the facing pages together, page 30 and 31. Anything through question number 13 that you would like to ask about? Anything through 13? Yeah. Number 2. It says in number 2 that in this diagram, and we can see this here, the spheres start off 100 meters apart. I want to know what is the horizontal separation of the spheres at the end of 1.5 seconds. So if I think no gravity, that's our horizontal direction, this projectile will end up here, this one will end up here. And I want to know how far apart are those two locations. In the horizontal direction, we can use this equation to figure out how each of them moves, but the 1/2 AT squared term is going to drop out because the A is 0. So what I'm going to do to figure out how far each of them moved outwards in the direction of their motion is just multiply their speed by the time. 30 times 1.5 is 45. So that's 45 meters. 10 times 1.5 is 15. So to get this distance here, I'm going to take 100, subtract 45, and subtract 15, which gives me 40 meters. Anything else through 13? Number 9. All right, I want you to compare the times it takes these balls to get to the ground. Notice it says they both start from the same height. That's all I need to know. Doesn't matter how fast I'm throwing them outward, they will fall to the ground together, which means since they are falling the same vertical distance, they get to the ground in the same time. They have the same height, so they get to the ground in the same time. Anything else through 13? All right, let's go to pages 32 and 33 then, please. Anything on those two pages, which gets us through question 21. No? All right, let's look at the next two pages through question 28. Anything you want to ask about through 28? 22. Okay. I want you to find the set of graphs which shows the horizontal motion of the ball. The ball is going to move horizontally with the bike even after you release it. And as it moves horizontally, because there's no gravity in the horizontal direction, it's going to travel outward with a constant velocity to the right. So I need graphs which show that that velocity is a rightward constant velocity. Constant velocity on a distance time graph is a diagonal line. On a velocity or speed time graph, it's a horizontal line, which means that's going to narrow it down to choice 1 and choice 4. It cannot be choice 4, though, because there's a negative slope. That would mean it's going left. This positive slope tells us it is moving right, so it's got to be choice 1. Dan? Sure. Okay. So we're telling you that we are firing it upward and horizontally. So 1 and 2 are out because they don't show up and right. These both have up and right. And if I were to draw those components head to tail, they would look like this. Now it's to scale. Look at the values. The vertical value is 5 and the horizontal value is 2, which means the upward piece is bigger than the horizontal piece. Which one has a bigger upward piece? And that's your answer. Anything else through question 28? Anything else through 28? How many of these questions are going to show up on your test Monday? 10. That's right. 10 of these multiple choice will be there on Monday, or extremely similar to it. No? All right. How about the next 2 pages? Let's just finish it out. Anything through 40, because there's only one on the following page, number 40. Anything you want me to go over? Any other multiple choice questions, Chang? 34. Okay, let's look at 34, which is showing this baseball bat hitting this baseball at an angle. And I want to know which angle gives it the largest horizontal distance. That's the range. These angles we investigated in lab 11 with the PhET simulation. And we also talked about it in class. The one that always makes it go out the furthest is always 45. You just have to remember that. It's always 45, giving you the largest range, the largest dx. Josh? I'm sorry, 35? Okay. So in 35, I want to know what is the speed of the tennis ball. When I say speed at the launch, it's just the VI. Notice I'm giving you the X and the Y components. So you're going to work backwards here. I'm going to redraw them head to tail like we talked about in class. There's the X. There's the Y. Each of these is 9.0 meters per second. When I talk about the launch speed, though, this is what I'm talking about. I'm talking about the hypotenuse, the VI. How are you going to get that if you have these 2 sides of a right triangle? Use your Pythagorean theorem. 9 squared plus 9 squared. Take the square root of that. And I believe that gives you 13 meters per second. It's got to be bigger than 9. Yep, 12.7, which is roughly 13 with the 2 sig figs. Okay, anything else you would like to ask about? All right, let's look at the show work. Number 1, The final answer is 32 meters. Number 2A is 0.500 seconds, and part B is 0.800 meters per second. And the last question, number 3, part A is 32 meters, and part B is 210 meters. Do you want to go over any of those? Josh? 3A. All right. I want to know in number 3A how high this goes. All right. So let's make sure we know what we're doing. First of all, in this question, I'm giving you the initial speed as 49 meters per second, and the launch angle is 30.0 degrees. We know this is going to go up and out. Okay. So here is your dy, the maximum value. There is your time. That is the range dx. Before we do anything else, we better break up this speed because you cannot use the 49 meters per second in any calculations to find any of these things. You're going to break it up. So here is that 49 meters per second. This is your VI in the X and your VI in the Y. That angle is 30.0 degrees. To get the X side of the triangle, we always use AX is A cosine theta, right off your reference table, page 6. That means I'm going to take 49 meters per second and multiply by the cosine of 30.0 degrees. With the 2 sig figs, because of the speed, that gives me a horizontal speed of 42 meters per second. To get the Y component, we use AY is A sine theta, or 49 meters per second sine 30.0 degrees, which gives us a vertical component with 2 sig figs of 25 meters per second. Now let me make my chart. What do I know about the horizontal and vertical directions? I always know my accelerations. 0 meter per second squared and negative 9.81 meter per second squared. I know the initial speeds. In the X, it's 42 meters per second. In the Y, it is 25 meters per second. Going up, positive. When I ask you how high it's going to go, that means I'm looking for this dy maximum. And I know at the top, it's still traveling sideways with the same speed, but it is going to stop, right? It's got to stop going up so it can then start to come around and come down. And I want to know what is the D. Now, I can do it without time, but I'm going to get the time first because I've told you that's what you always should be doing. So the first thing I want to do is find the time no matter what. Because in part A, I want how high it goes here. And in part B, I'm looking for that range, the dx. I don't know either D. So to get the time, notice that the y values for velocity change, the x ones don't. So I should be thinking about the y direction to help me get the time. Using an A, a VI, and a VF, which means I use VF is VI plus AT. So VF minus VI over A is going to help me get my time going up. So that is 0. Negative of positive 25 meters per second divided by negative 9.81 meter per second squared tells me that the time up is 2.5 seconds. But it also tells me that my total time, which is double that, is 5.0 seconds. So to get here, the time up is now 2.5 seconds, but to get here, it's 5.0 seconds. Now I can do part A to find how high it goes. And I've got 3 possible ways I can do it. I can show you all 3. Do you have a preference? How did you say you wanted to do it? What equation did you pick to get this height? D is VIT plus 1/2 AT squared. You have to have the half AT squared because if I'm looking for it in the Y direction, the A is not 0. It doesn't drop out. None of it drops out. So if I were to plug in, the VI I'm going to use is my positive 25 meters per second. The time has to be just from here to here, which I can see on the picture is the time up, 2.5 seconds, plus 1/2 of negative 9.81 meter per second squared times that 2.5 seconds, which would get squared, which gives us a maximum height of 32 meters. Then in part B, if I wanted you to find the range, that's D in the X direction, I use the same equation. But in the X direction, the acceleration is 0. So the half AT squared would drop out, which tells me that this distance would be the 42 meters per second horizontal speed. But here I have to use the whole time, 5.0 seconds, to go from here to here. So when I multiply that, I find that my range is 210 meters. And that's the entire question number 3. Okay. Anything else you'd like to ask about? Anyone need number 1 or number 2? Monday's test, the constructed response, will be 2 projectile motion problems with multiple parts. One of them is going to be an angled problem. And guess what the other one is? Come on. What's the other one going to be? If one is an angle, what's the other one? Horizontal. You already know what I'm going to ask you to find, because you got a whole packet full of them where I solve them with you. You're going to have to set them up exactly the way I showed you. And the directions will tell you to set it up that way. And setting it all up is what gets you the partial credit. The final answer only gets you like 1 out of 6 points. So if you're not setting it up, you are not going to pass it. Yep, that's part of the setup. And you can bet one of the questions I'm going to ask you to do is fill in a table. What do you know? Because if you can't make the table, you probably can't solve the questions correctly. If you can't tell me what you know, there's no way you're going to be able to solve for anything. Anything else that you want to ask about? All right, then let's put everything away. We're going to start Unit 6B. Since I got lots of extra time. I'm not going to give you 15 minutes for a study hall. Let's start Unit 6B, which is what I was going to do after your test on Monday. So please put everything away except your notebook, your reference table, and a pencil, please. There is no written assignment on this over the weekend. Your assignment over the weekend is to study and get ready for your test. For your test, you need to make sure that you bring a pen and a calculator. Pen and calculator. I'm sorry? No, I do not. You can tell me on your way out of class. I have no doubt, but you can tell me on the way out. Okay, Unit 6, as you can see, is about Newton's first law of motion. And Newton's first law of motion, yes, sir. Newton's first law of motion is actually known by 2 other names besides Newton's first law of motion. You'll need to know it by all of the names. Newton's first law is also called the law of inertia, which means we'll be learning what the word inertia means, but it's also called the law of equilibrium, which means we'll also be learning what the term equilibrium means. What I'll ask you to do with this, it is a conceptual topic, so there are no math problems with this, even though we'll be looking at different symbols that we use to abbreviate things on our reference table. Of course, the whole rest of the course is about force. And I asked you that you needed to know for today what we meant by a force. So, of course, that's still applicable. But then I need you to be able to state Newton's first law and explain it to like a kindergartner. I'll then ask you to define the terms inertia and mass, and then explain the difference between something called a net force and something called equilibrium. So just to review what we discussed yesterday, forces are pushes and pulls. We abbreviate them with a capital F. We measure them in newtons, which is a derived unit equivalent to a kilogram times a meter per second squared, and they're vectors, so we're going to draw them with arrows. Let's now talk about the new stuff, Newton's first law. And this law should not be new to you. Your middle school science teachers are very good at having you memorize this law and reciting it back. An object at rest remains at rest. An object that's moving remains in motion. There you go. That's the middle school version. Now that you're in high school, we have to know a lot more about it than just reciting it back. There's a lot more to it. So if you have an object that is at rest, it wants to remain at rest. But if it's moving, it wants to keep moving at a constant speed in a straight line. So we're not just going to say an object in motion stays in motion. You got to tell me how it stays in motion. It keeps moving with a constant speed in a straight line. And both of those things will be true so long as the object is not being acted upon by something called an unbalanced force. Remember, what we're doing now is we are talking about why objects move the way they do. Objects, will move the way they do because forces are acting on them. And we're telling you that it will keep a constant velocity or no velocity if there isn't an unbalanced force. So let's talk a little bit about what that means, an unbalanced force. Forces can either be balanced or they could be unbalanced. Unbalanced meaning not balanced. Just very conceptually here. Take a look at this. Let's say I have an object and there is 5 newtons of force pulling that object to the right. If this is a balanced force situation, is this balanced right now? 5 to the right would have to be balanced with 5 to the left. Okay. So showing this is an indication that we have a balanced force. These forces are balanced, equal and opposite. How about if I applied that one of the 5 newtons up and right? If this were balanced, what would I see? How much? 5 newtons would also be opposing it going down and left. This is also balanced. What about this by itself? Is this balanced or unbalanced? This is unbalanced. What Newton's first law is describing are these situations. This is what is described in Newton's first law of motion. And what Sir Isaac Newton said was that when these forces balance out, you do not change your motion. And when you don't change your motion, it means that no matter what, your acceleration is 0 meters per second squared. That's what he told us. Now, do I know if these objects are at rest or moving with a constant velocity? No. All I know is that when the forces balance out, we do not change our motion. Whatever that motion is will remain the same. It will not change. We do not accelerate. Once we have an unbalanced force situation, then motion changes. And that is his second law, which we'll be talking about later. So there are really two parts to this law, as you read. The primary thing that's true no matter what is that in this law, the forces on an object must balance out, like I was showing you in those pictures. They have to balance out. If the forces are balanced and the object's at rest when those forces balance out, it means that your speed is 0 meters per second and it stays 0 meters per second. We don't need a calculator, Bryce, for any of this. Put it away. If we are moving, that means your speed is not 0 meters per second. Your speed is going to remain whatever that non-zero value is, and your direction is not going to change. So if I'm in my car driving, this is the situation where my steering wheel is not changing direction and I'm on cruise control. That's the only situation. I'm not speeding up, I'm not slowing down, and I'm not turning the wheel. Those would be an unbalanced situation. Balanced forces imply that your speed doesn't change, nor does the direction you're traveling in. In other words, you're not accelerating. So the universal truths with this law are no accelerations and balanced forces. But that's a flow chart which will help you understand both situations. Because I'm going to give you descriptions of objects and what they're doing, and you're going to have to tell me whether the forces are balanced or not. And how do you know? Okay. Everybody all set with the flow chart? Okay, so let's look at some examples. What does this mean when we have balanced forces in terms of our motion? When we have balanced forces, if you're not moving, it means your velocity is 0 meters per second, and it will always be 0 meters per second, period. If you're moving at 5 meters per second in the positive direction and the forces on you are balanced, you're going to keep moving at 5 meters per second in the positive direction. That's not going to change. You're not going to accelerate. Likewise, if you're traveling to the left at 2 meters per second and the forces on you are balanced, you'll keep going at 2 meters per second to the left. So anytime you see a constant velocity, the forces on that object are balanced. Why does it move with a constant velocity? Because the forces are balanced. That's the reason why. Remember, this is all about why the objects are moving the way they do, because the forces on them balance out. Which means you have equal forces in opposite directions to balance. So, as we just said, in this law, that all objects are going to try to resist a change to their state of motion. In other words, they want to just keep doing what they're doing. If they're moving, they want to keep moving with a constant speed in a straight line. If they don't do that, it's because something forced them to change. Just like people. People want to keep doing what they're doing until they are forced to change. So this brings us to the concept known as inertia. What is inertia? As you can see here on the call out on the top right of the screen, inertia refers to a measurement, a quantity, which is determined solely by the mass of the object. And one of the questions you'll see on your June Regents exam is about inertia. What is it? What is it? So, what is inertia? It is the tendency of an object to resist a change in motion. Change in motion is acceleration. So we're talking about things trying to resist an acceleration. And as we just said, it's dependent solely on your mass. It's dependent solely upon your mass, which means the more massive you are, the more inertia you have. Or the less mass you have, the less inertia you have. The more easily we can get you to change your motion. So let's just finish off with the discussion, therefore, of what is mass. We've been talking about mass since the beginning in September, but mass refers to how much matter is in an object. And when we refer to matter, we measure it in kilograms in the metric system, which we know is abbreviated as lowercase kg. Now be careful. Mass and weight are not the same things. And this is something that you have been programmed since a little kid here in the United States that they are the same things. They are not. Common everyday English can mess you up in terms of physics. People get it wrong. So we have to break you of that habit here in the class. Mass and weight are not the same things. Mass is how much stuff is inside of you. Your weight, we learned yesterday, is the force of the earth pulling on you, the force of gravity pulling on you. And since weight is a force, in the metric system, we measure it in newtons. English system is pounds. Mass is always kilograms. They're not even measured in the same units. So how could they be the same things? They're not. One last thing. On your reference table, in the right-hand column, oops, hold on, one last thing. Check off, please, the lowercase m, which refers to mass, and indicate that is in kilograms, kgs. Once you have that, you're all set for today. I'll see you Monday for your test with a pen and a calculator. Have a great weekend.